Hello and welcome to physics. In our next section we will be looking at moments. Wait, give me a moment. Does moment mean moment in time, or does moment have a different definition in physics? Another way to define a moment is we would call it a turning effect. Okay, so if I had to loosen a nut like this with my fingers, I would have to make it turn. Okay. And that might be quite difficult if you've ever tried that when it's inside a bolt or a nut or something like that and we need to loosen it. So as most of you know, that if you see a shape like this, you can use a spanner and you make the spanner, this is a shifting spanner, so it's an adjustable spanner, and you put it over there, but we don't kind of hold it over here. Okay. If I hold it here, I can turn it, but it's going to be very difficult. But the moment I hold it here, it becomes much easier. And let's say I've got a car or something like that, and I'm struggling to loosen the nuts. If I connect a stick or tie a stick, and I make this thing even more longer, and I hold it, let's say further down, then it becomes also easier to turn. So the further I am away from the nut, the easier it would be to turn it. And we call this turning effect a moment. Now the formula for a moment is the moment is equal to the force times the distance. Okay. Now we know that force is a scalar of a vector, so force can be a positive or a negative depending on the direction. Distance here is only a scalar, meaning that moment will be a vector. And how do we calculate that? A positive times a positive becomes positive. Positive times a negative becomes a negative. So moments can be positive or negative. Okay, and we know that moments will have a direction also. Okay, now what I should have added here is that it's not just the distance, but it is the perpendicular distance. So the force must be perpendicular to the distance that we're measuring. So if we look at this, okay, I'm applying a force, okay, I'm applying a force downwards. How far is that force? If we had to draw that, okay, here I've drawn something similar, so if I push upwards here, okay, the force is perpendicular to, so if I just pull on it, it's not going to turn. If I push on it, it's not going to turn. So any force in line with this beam or this distance is not going to have an effect. So if I pull on it or if I push on it, imagine you have a door and you kind of, so here's your door, and instead of pushing it like this, you push towards the wall. Okay, instead of opening the door or closing the door, you just push on the door. It's not going to move. Okay, so pushing towards this pivot and away from the pivot, we call this the pivot, the point where it is connected. Okay, you spell it P-I-V-O-T. It's not going to cause a turning effect. It's when I push at a 90-degree angle where I get the biggest effect. Now if I push like this, I might have an effect, but if I push like that, the effect would be much bigger. Okay, so it's the perpendicular distance times the force. So the further I move my force away, the bigger the turning effect would be. Now, if we think about it, let's say this nut has got a needs a moment of 10 Newton meter. Newtons times meters. The unit for moment is newtons times meters is Newton meter. So let's say this nut needs 10 Newton meters. Okay, then I can do the following. I can say I can apply a force of 10 Newton at 1 meter. Okay, so when it's very, very close, I can apply a big force. Okay, obviously this spanner is not a meter. Or I can say 5 newtons times 2 meters. Okay, so instead of holding it there, okay, if I move it backwards, I can apply much less force but have the same loosening effect. Or I can even say 1 newton times 10 meters. And all of them will have the same turning effect, the same moment. Okay? And what this gives us a mechanical advantage. By using less force, we can still do the same amount of work or move a certain object. Next, we will look at these mechanical advantages or these mechanisms. We call them levers. So let's say I want to move a very, very, very big rock. Okay. If I put a little stick in there and I wedge a plank or a piece of rod and I push down here, I can move the rock, and we call this a lever. Now we use levers very, very often in very everyday life examples. Okay, so the longer the rod is, the less force I have to apply. So if I push here, I'm going to push much harder than when I push here. And if I extend this and I push there, it's going to be much less force. So the longer the lever is, the less force is needed. So once again, so let's say this is 100 Newton meters, a turning effect of 100 Newton meters needed to lift this. Okay, what is Newton meters? It means 100 Newton at a distance of 1 meter. Okay, so if I'm 1 meter away, I'm going to have to push down 100 Newton to lift up this object. If I'm 2 meters away, 50 times 2 also gives me 100. I only have to apply 50 Newton. Okay, and the further I move back from this point, this is called my pivot, or that's the point where we wedge it around. Okay, the further I move away from that, the less force is needed to move this object. We get 3 types of levers. The first type lever is type 1 lever, or a class 1 lever, and that is different examples. A scissor is a class 1. So what is a class 1? When we have our pivot, or also known as a fulcrum, in the middle, we have our force on the one side, also known as the effort, and we have the load on the other side. So where I apply the force and where I do the work is on 2 opposite sides. Now, if we think about here, there is our tin. We lift up our tin by pushing down, and where the screwdriver's tip is, that's the fulcrum, the point where we make it move. We have a scissor. I apply a force on the side where this is, and the work is being done here at the load. And then also lastly, the lever that I've shown you just now, okay, where we use a stick, a stone, to make a pivot. We push down on the one side and we lift it up on the other side. Class 2 levers would be where our pivot is in the front, our load is in the middle, and our effort is at the back. And a classic example of that would be a wheelbarrow. Okay, so we make our pivot, or our fulcrum would be here. My force downwards is here and my force upwards is there, and my upwards force is further away from my pivot, so therefore I have to use less force. The next example is a nutcracker, okay, where we put our nuts in close and we push at the back. Another example is a normal car door, okay, the load is the weight of the door, we push it here at the handle, and the fulcrum is the hinge around which the door moves. Class 3 lever is now where the fulcrum or the pivot is in the front, the effort is in the middle, and the load is at the back. Okay, so we going to look here. The one example is a broom, okay, where the load, the work being done is at the tip. The middle is where I apply the effort, and I hold my other hand at the top. Okay, not this clear example. Tweezer, much more understandable. Here is a pry tong, okay, which also works similarly, and a stick, a fish stick, so fishing rod, okay, that's the right word. And you apply the effort in the middle, and the load is at the tip. Okay, so the class 3, the load is at the back and the effort is in the middle. Class 2, the load is in the middle and the effort's at the back. So the force that you apply and the object that you're physically moving. So we've said that a lever is or a moment is a vector, so that means it has a direction. The direction that we're going to look at, if I push it upwards here and I pivot it there, it's going to go in a circular direction. So let's see here. If I put my finger there, okay, and I push, okay, so when I push upwards, it's going to rotate. The object is going to rotate. So this is from the side. The object rotates. It doesn't go fly up. So if I hold it here, it doesn't fly up in the air like I'm pushing it up on both sides. It rotates, and that's why it's called a turning effect. So we classify the direction not as up and down, but we will speak about clockwise. So this would go that way. That's anti-clockwise. And if I push down on the object here, so here I am pushing down on the object, it goes clockwise. Now, this brings us to the next part where we can balance objects on a class 1 lever called a seesaw. Okay, so here I have a person sitting, and there I have a person sitting, and we have a nice seesaw. Which way is this one causing this beam to move? And what we do is we put a pen or something and we just push it in the direction, and we can see that that is an anti-clockwise motion. So this one is anti-clockwise, and therefore on this side, if we push it down, this one is clockwise. Now, if you guys know a seesaw, this can even balance each other, and that would be what we call a system in equilibrium, when these two moments balance each other. So now we're going to move on to the principle of moments. So we've discussed equilibrium before, and we said that is when forces balance, right? Okay, so let's say I have an object and I push upwards with 10 Newton and downwards with 10 Newton. What is the result of equilibrium? It means there is no movement. Okay, so it's not going to go up or it's not going to go down. So we all agree that that is in equilibrium. So what if we replace our object with a stick? If I pull up here and pull up there with 10 Newton, it's not going to move anywhere. There's no movement. Okay, and we said that forces are balanced when the forces up is equal to the forces down. Okay, it's just forces up is equal to the forces down, and the forces to the right is equal to the forces to the left. Now obviously there's no forces to the right or the left here, so this would technically be balanced. But what would happen if I do this? There is still an upwards force and a downwards force, but now my forces are not together. They're opposite to each other, and that's going to cause a turning effect. So to be in equilibrium, not only do we need our forces to be balanced, but we also have a second condition that our moments must balance. And that means my clockwise moments, my moments clockwise must be equal to my moments anti-clockwise. So, question. Is it possible if you have a friend that weighs 80 kilograms to play on a seesaw with his brother or sister that weighs 40 kilograms? Okay? Yes, it is. Because it's not the masses that we're balancing the moments. Okay? The mass we can convert in weight, so that would be 800 Newton. How do we get to Newton again? We times it with 10, and this would be 400 Newton. Okay, if we times the mass with 10. Now, if I put that child here 2 meters away from, okay, and it pushes down in a clockwise direction, how do I know it's clockwise? Put my pen there. So this is going to be clockwise, CW. Okay, so 400 times 2 gives me 800 Newton meters. Okay, and 800 is what I need to balance it. So what do? I put my brother or sister, which is heavier, 1 meter away, because 800 times 1 is also 800 Newton meters, and this is anti-clockwise. So the moment my clockwise moment and my anti-clockwise moment is equal, our system is in equilibrium. It's not moving up, not moving down, not moving to the left, not moving to the right, and it's not rotating. So that is what we call equilibrium. And the principle of moment says that an object is in equilibrium when its clockwise moment is equal to its anti-clockwise moment, and when all the forces are balanced.